dear students, you already know about machine learning methods that can solve problems of regression and classification where you want to map objects to labels. Generative models push the difficulty in the problem to the next level. We now can learn the whole probability distribution. The terminology here is a bit unsettled. A generative model can learn the probability density explicitly, or it can learn to sample from the distribution, or it can do both. Generative models have seen rapid evolution in the last 10 years and were able to achieve some magnificent accomplishments. Let us take a look at some of them. Like many things in deep learning, the last sprint in generative models development began with images. In just 6 years, 1.5 LHC runs, we went from the creepy black and white modern art to the left to the photorealistic images on the right. Mind you, a meager 256 by 256 pixels image is an object with over 65,000 of dimensions, and we can now learn the probability distribution in this space. Not only we can generate images, we can also manipulate them. We can seamlessly replace a face with one person with the face of another person on a photo or video. We can animate a face of a person to make them appear to say anything. Just a few years ago, movie studios were paying millions for this, and now you can do this with the open source code and a little bit of CPU time or GPU time. The next milestone is text generation. Although it's not quite human level, modern computer can have a decent simulacrum of a conversation. Let us see a demo how it works. Let us look at what modern text generation model can do for us. And as an example, let us ask it a deeply philosophical question: what is the purpose of life? So we write the beginning of the answer: the purpose of life is our physical state of being. Our experience of that physical state will not be determined by what we have seen. And it is as certain as is possible that we are not living in an environment with only the physical attributes of the human being. Well, if you ask me, that is a pretty coherent text as much as the philosophical text go. The last glaring piece is the voice. Computers can understand you and synthesize speech that is almost not creepy. Oh, let us see an example.
Tell me a joke about physics.
A photon checks into a hotel, and when the bellhop asks if he can help with its luggage, the photon says, "I don't have any, because I'm traveling light."
Well, see? It even knows a tiny little bit about physics. What are the common things about those applications? First and foremost, there is a huge amount of similar data available, along with the computing power to process it. Then, consumer applications are forgiving. When generating images, it's not crucially important to get distribution in the 65,000 dimensions right. It is important that the images are realistic and diverse. In high-energy physics, we have the first two bullets and absolutely cannot stand for the last one. So, let us explore the applications for generative models in our world of physics. First of all, I'd like to be a bit of a boring theoretician that I am, that a humble histogram is a model which approximates probability distribution, and therefore it is a generative model. And all of you have used it. No further introduction needed at this point. Then there is an improvement of the idea of histogram. It's kernel density estimation. We will cover it in the next section, but in a nutshell, it is still applicable only in low dimensions, but it provides a smoother estimate of probability density than a histogram. Then we have the complicated models, which allow us to generate very complex objects, like I covered in the beginning of my presentation, where let us consider where we can put them in physics. Obviously, for generating the data, like we do when we are generating Monte Carlo simulations. And there is a challenge for us, at least at the LHCb experiment. If we stick to the simulation method that we have now, we will not be able to maintain the physics performance after the LHC upgrade, when the LHCb luminosity will increase fivefold. So, unless we want our results to be dominated by the limitations of the available computing power and thus the simulated data, we need to develop new, better methods for simulation. In this plot, in green, you have the amount of resources we would need if we use the simulation methods we have now. And in red, you have the projected amount of resources available. And it's easy to say that they do not match. So we need better methods, we need better new methods. And generative models offer an interesting approach to get it. Let us see. In high-energy physics simulation, in very basic sense, can be separated into three stages. On the first stage, we simulate the fundamental interactions, the quantum chromodynamics, where we simulate the collision of particles, we simulate the decays over secondary particles, until we reach the stage where all particles are long-lived enough, of the long-lived enough particles which reach the detector. Then we simulate the interaction with the detector using usually the Jean-4 software. And finally, after we obtain the detector response to our particles, we move to the reconstruction stage. We use the same algorithms that we use to processing the real data in order to read physical objects from the raw detector response. And then we use those physical objects to do analysis, or to make physical discoveries. And there are two key observations on this scheme. First of all, this step, the interaction of stable particles with the detector, takes the most computing time. And second, the detector stays the same for every of the billions events that we simulate. And moreover, the stable particles which reach the detector also are the same stable particles. Well, they just have different tracks, but they are the same particles which interact with the same processes with the same detector. So it seems like a good job for a generative model. If we use the parameters of the tracks as the inputs to the generator, and we use a generative model to simulate the detector response, we might be able to replace parts of this diagram with machine learning. First of all, we can do it like this, where we map the track parameters to the response of the detector to such tracks. Or we can do it like this way, where we skip simulating the raw detector response and directly simulate how the tracks will look after reconstruction. In a nutshell, particle identification is the most expensive part in simulation of high-energy physics detector, and it works like this. Charge tracks leave trace in the tracking system. Then they emit photons which are detected by the Cherenkov detectors. Then electrons and hadrons are absorbed by the respective calorimeters. And finally, muon chambers detect the muons, which pass through the whole detector. And we can simulate different parts of this particle identification process with different caveats and different kinds of models. Historically, the first was simulating the calorimeter responses. This is one of the latest, most state-of-the-art papers on the subject. Though they have the ATLAS calorimeter, they're able to achieve a pretty decent results in terms of physical observables. So the events which they generate, they look very close to the events which can be simulated with Gen4, and they are able to capture the complicated geometry of the ATLAS calorimeter with its different sizes of cells and different alignments of cells. So their model has 4 layers with 266 output channels, and they're able to simulate the events in full 3D. So their task is even more difficult than the task of generating images, which is common for machine learning. The other approach, the fully parametric simulation, is explored by the LHCb experiment, among others. What we do here? We begin with the simulation of the physics, so where we propagate the particles through the detector, and then we obtain track parameters from it, the momentum, the pseudo-rapidity, the event occupancy. Then we have generative models which simulate the response of the Cherenkov detector and the muon subsystem. Then we feed the outputs of those generative models through a couple of generative models which simulate the response of the algorithms which combine this information into the final particle identification decisions. So in the end, we have tracks, and we have the particle class likelihoods, which can be directly used for analysis, directly from the machine learning based simulation. So this is a part of this scheme, namely the simulation of the Cherenkov detector. To the left, we have the plots which show the correspondence between the real data and a simulation for k-on likelihoods, for k-on and pions. As you can see, the correspondence is pretty decent. To the right, you have the quantification of the left plot, in which we use the physical nature of the particle likelihood variables, because particle likelihood variables are the output of some classifier. So they provide us with information to make a decision about particle type, and we can use the metrics about classification, which you already know, to study their performance. And what we expect is that a simulated detector has the same performance, not better, not worse, than the real detector. To do this, we make bins in momentum and pseudo-rapidity, and in each bin, we calculate area under ROC curve for the corresponding, for the events, for the tracks which fall into this bin, the real and the simulated tracks. And on these plots, you have the difference in those areas on the ROC curve normalized by the statistical uncertainty dictated by the finite training sample. As you can see, in many bins, the model achieves the result which is close to the best possible on this amount of data, where the difference is the same magnitude as the uncertainty of the measurement. In the bins where we have fewer data, the difference is a bit higher, but overall, again, we see an excellent correspondence. To wrap this part up, that fast simulation with machine learning has advantages. First of all, it is really fast. It's 2 orders of magnitude speed up compared to Gen 4 for simulation. Secondly, it can be trained on data, not Monte Carlo. Therefore, you can, in principle, improve not only speed but also quality of simulated data. For the hard to analyze, for the hard to simulate subdetectors like the rich subdetector. And finally, once you have a machine learning based fast simulation model, it is trivially easy to update it in case of detector modernization or calibration change. You only need to retrain it on new data, unlike in case of the expert models, where any update would require an expert to go through your model and to again create, for example, simplified geometry. There are a couple of caveats about these methods. First of all, they require training data. And this means that in order to obtain this speed up, you either need to generate quite a lot of Monte Carlo simulation with the tools that you have, or you need to use the calibration data which is available only when the detector starts and the algorithms for data processing are in place. Meaning that these methods would have limited utility in the case of not data analysis but detector development. And secondly, these methods, like any methods of simulation, suffer from systematic uncertainty. Just like Gen 4 is imperfect in describing certain aspects of interactions of particles with the detector, machine learning based simulation also have their deficiencies. The main source is not the imperfection of machine learning itself, as we have seen on the plots, the correspondence between the distributions you want to learn and the learned outcome is pretty good. So machine learning algorithms do their job. The primary source is the parametrization, because in case you use a fully parametric model, you treat each track independently, which is not the case in the real life, where if 2 tracks are close together, then they might smear the identification of one another, and with fully parametric simulation we miss this effect. So we have very fast way to obtain more data, but we add another task for physics analysis when we use it. Now finally, the conclusion of this introduction is that generative models are a very fast growing subject in the current ML research, and there are a lot of entertaining applications for them. There are promising applications for energy physics. To my knowledge, there haven't been a finalized physics analysis based on the models which I introduced today. However, all of major CERN collaborations are working on fully parametric simulations. So, and all of them report promising results. So we expect to see in the near future that those models are used in production, and we invite you to take part in it. And well, finally, stay tuned for the next lectures in this section. Today and tomorrow we shall cover the methods which allow you to create those models yourself. Thank you.